Okay, so good morning. Let's resume our discussion on the interaction of electromagnetic wave normal incident on an interface between one media and then with another media. Before we discuss this, and I got some question. Then the student asked why we bother to have so many formulations. Okay. Question is, as a human being, do we need to have a language? Do we need to have a literature? Let's say any letters and words that can carry on all the heritage, right? And the same as in our science and engineering subject, right? We need to have a formula to convey the information precisely, describe it, right? And also, this is a formula is more than just a language. It's also a tool, right? That can relate all these nature relations, right? You see, for example, this is a solution we are using is we can justify that satisfy Maxwell equations, right? So all this we can also from the formula we already learned, we can derive more useful formula, right, for to use. So no question. You see, if we don't discuss using these formulas, we have no place to go. All right, okay. Now let's continue what we stopped last week. Is we have one media we call media one, like characterized by permittivity one and permeability one, right? Then we have medium two that also characterized by permittivity and permeability, but different from those in medium one. Right? We assume the wave, the electromagnetic wave from left, can see my hand, from left to right, okay, from infinite left, and then propagating toward right direction or toward the z direction, and hit on the interface. Okay, this is the interface, hit on the interface. How we describe the wave, the propagation direction, okay, then here, right, we use z, and then the propagation constant that we use the in medium one, right? So everything is in logic, right? And minus j means propagating in positive z direction, right? J means beta z is a phase, right? This is a phase. Physical. And what is the polarization direction in this wave? Polarization direction is polarized in x direction, okay? Polarized in x direction, right? So I draw here, polarized in x direction. Then mathematically I use unit vector to describe the field polarized in x direction. Right? Now I have arbitrary, this is arbitrary magnitude. This is magnitude, but this magnitude can be, in general, is complex. Okay, this could be complex, right? Then this is we describe electrical field first. Then once we describe electrical field, we can describe magnetic field because the phase term is the same, okay? But the magnitude follow Ohm's law, okay? But this Ohm's law, I put a quotation, okay? This is a name called by me, right? But you see, it's just for easy to remember. And how to determine the direction of polarization for magnetic field? We learned for plane wave, we follow the right-hand rule. From electrical field, magnetic field, then some point to the direction of propagation. All right, direction of propagation. So this is always the case if you describe a plane wave, right? Okay. Then what we do is, when the wave hits on the wall, okay, we expect we have a reflected wave. We indicate using R, mean reflected wave, right? So I don't repeat why I describe reflected wave in this way. I just assume polarization of reflected electric field is the same as the incident wave. But this is a plus because reflected wave propagating in minus z direction, right? Then similarly, we can find magnetic field. Magnetic field must polarize in minus z direction because we follow the right-hand rule. Okay, this is the one reflected wave. We also have a wave penetrate into the medium 2. Okay, we call the transmitted wave. We use a subscript T. Okay, and also propagate in minus z direction. Pay attention. Okay, we use beta 2 instead of beta 1 because incident wave and reflected wave both happen in medium 1. So I use the propagation constant in medium 1, right? For transmit wave that propagating in medium 2, of course, I have to use wave number in medium 2. So I indicate by subscript 2, right? And similarly, we can write magnetic field, okay? Then we have 3 quantities we need to find a relation, right? One is incident wave, right? We have incident wave and also for, okay, so we don't write magnetic field. So because once we know in electrical field and divided by wave, intrinsic wave impedance, we know magnetic field magnitude. We also have reflected wave magnitude. We have a wave magnitude for the wave propagating, okay, penetrate into medium 2, right? So this is magnitude. We need to find a relation between them, okay? We assume this is no, okay? So this is a unknown. Okay, then we have 2 unknowns. We expect to have 2 equations, right? Then how to find their relations? Okay, then we add incident wave, okay, plus reflected wave in medium 1, okay, in medium 1. Then we have this in medium 2, right? In medium 2. Then this is electric field. Okay. When we add, this is a vector, right? We must vector add vector. So that means only same component we can add, not same component we cannot add. All right. We add electrical field, we add magnetic field. Okay. In 2 different medium. And remember, we learned the basic property of electromagnetic field, okay, across the interface between 2 different media, okay? Then one of the important conclusion is the tangential field, okay, must in 2 different media must equal, okay? I put the vector because tangential field could be vector, right? They're equal, right? And for magnetic field, okay, for magnetic field, then we have to have normal direction, okay. This is magnetic field in medium 1, magnetic field in medium 2. I use N cross. Any field component will be tangential component. So this equal to a current, okay? That is surface current, okay, surface current. Because current cannot flow on a dielectric interface. So if I don't have any mechanism that can support current, so this equal to 0. That means, okay, that means the tangential magnetic field equal. Okay, that means tangential magnetic field equal. Then we use the tangential field equal on both sides. Okay, equal. That means this is Z equal to 0, right? At interface. And magnetic field equal. This is magnetic field equal. We have two relations. One is this relation, one is this relation. And I have a verbal assignment gave to our student is from this simple two equations, we can easily derive the two relations. From now on, so you can see I already slowed down my discussion because suppose this material should be finished last week, but I think it's too important. I should say 70–80% of questions in our final exam start from this lesson, okay? And then this is a so important concept. So I like to slow down, right? I like to slow down. So therefore, we can find, we call reflection coefficient, okay? This reflection coefficient, I use. This reflection coefficient is describe what is a reflect coefficient in terms of incident field coefficient, right? This is how we define reflect. We can define transmission coefficient, okay? The transmission coefficient describe how to determine the magnitude of transmitted wave in terms of incident wave, right? Okay, these two coefficients describe the reflecting wave and incident wave. What is the property when the field happened right on the interface? Okay, right on the interface. This is how we determine, right? Because ERO is not remember, okay? This is not a field, okay? This is it is E field only at Z equal to 0. Do you agree? You see, look at the mathematical expression. Reflected wave, look at this. Reflected wave, right? Only when Z equal to 0, this equal to 1, right? So of course we know the polarization direction. So this component only refer to the field on the boundary, okay? It is a coefficient, I agree. You can call this a coefficient, Okay, but only if you look at it as a coefficient, logically, we never find a reflection for a coefficient. Okay, we find a reflected wave at a certain location. This is a physically makes sense. Okay, if you say coefficient reflection of a coefficient, we are not interested in that. We have no such physical quantity. Okay, so when we deal with this quantity, okay, remember this is the reflected wave when xi equal to 0, or it's the boundary. Okay, only at the boundary that makes sense. So that means this I will specifically mean reflection coefficient at boundary. Okay, which is xi equal to 0. All right, this is very important because very soon you will see reflection coefficient at different location. The mathematical expression might be different. Okay, so I emphasize this is only reflection coefficient on the boundary. Okay. Another important observation. Okay, another important the observation is if you look at gamma. In this case, that's determined by eta 2, which is a real number for now, okay? For now, it is a real number. Because for lossless case, gamma 2 is gamma 1, gamma, sorry, it's not gamma, it's eta 1, eta 2 are real number. So reflection coefficient on the boundary is eta 2 minus eta 1, eta 2 plus eta 1. So it's also a real number. It's also a real number, right? This is only for lossless case. If you recall, even last week we discussed, if you recall, in general, if we have a conductivity in the medium, the intrinsic wave impedance is a complex number, okay? But for now, we just, for easy discussion, we consider it is real, okay? So this is what I like to discuss. This is the first things, okay? I said reflection coefficient is on the boundary, this value, right? The second, this is real, okay? The third things, we call discussion. Okay, the third things we can very easy to remember. Okay, this reflection coefficient. Okay, this reflection coefficient is a very simple, very easy formula. We must remember. Okay, because by the way, final exam, university ask, okay, all the students in Hong Kong must participate, must attend face-to-face final exam. Okay, so this is a requirement. I think your other courses also has the same requirement. Okay, so we have no room to discuss. For those students, and if you're not in Hong Kong, you prove it, and then we will arrange the online exam. The question paper is the same, okay? But for those students, we are going to take online final exam. We will arrange time before exam. We will arrange time to help you to set up your webcam setup, okay? we need to make sure you see your webcam or your mobile phone is placed in an appropriate location, okay, that can comply university requirement. All right. Okay, then in the final exam, and then I will have no we will have no information sheet. Okay, no cash sheet is allowed. The reason, let me explain the reason. The reason is we mislead our student, and then they consider they can write everything in the sheet and then don't need to understand. This is very, very wrong. And then I don't like to mislead our student. And if you some very, you say, a little bit complex equation, if you need, definitely I will provide you, okay, in the question sheet. So don't worry about that. But however, you see, this formula to calculate reflection coefficient, you see, very easy to remember that only related to intrinsic wave impedance, eta, right? So in lossless case, eta is mu epsilon 0, right? Or if you have different medium, okay? So as simple as this, right? Then if you look at lossy case, so don't worry, I will provide you, right? But however, you see the reflection coefficient, first, if you don't remember it, takes less than 1 minute, you can derive it, okay? By applying boundary condition, right? If you like to remember it, very easy, because gamma 2 is the wave impedance on medium 2 side, okay? On medium 2 side, right? This is eta 2. Is what you see, okay? What now you have, okay? This is your eyes, okay? This is your eye. What you see is eta 2, right? What you see is eta 2. And yourself is eta 1. So eta 2 also. This is eta 2 minus eta 1. Eta 2 plus eta 1. So very easy to remember, right? Okay. Now, once you know the reflection coefficient, you know transmission coefficient by using the second equation, right? Okay. So now we have, I spent too much time on this. Now we have reflection coefficient, transmission coefficient. We can add total field in medium 1, that equal to incident wave, reflected wave, right? But now we know how to express the coefficient of reflected wave. The coefficient is also happen to be the field on the boundary, okay? The reflection coefficient can be used to find reflected wave, the magnitude of reflected wave, right? So we just substitute reflection coefficient definition into this. This is very straightforward, okay? Then let's do a little bit more. One more step is we extract this term out of the bracket, okay, which is this. So this term become 2 times. This become 2 times, right? So 2 times means what? This is if I have a boundary, okay? If I have a boundary, then so if I have this distance is minus that, right? This distance is minus that. You see, because I go away from minus that, right? So that means the wave go one way and come back. So that means I have 2 times minus that and travel in beta 1. So that means, what is this? This is a reflection coefficient at minus that location. Okay. At minus that location. This is reflection coefficient. Okay. Reflection coefficient I have. So we will have a more general description anyway. So this is a total electric field. Similarly, we can find the total magnetic field, all right? Because once we know this relation, we have a minus sign to describe the magnetic field for reflected wave must polarize in minus y direction. Okay, we don't repeat this. And now let's have a further discussion. Okay, depend on when you upload your my handout. Here I add 0. I think that makes more sense because I added the last night. Okay. All right. Let's see. Gamma reflection coefficient equal to eta 2 minus eta 1, eta 2 plus eta 1. Okay. Then we know the electrical field. We know the electrical field. Okay. This is electrical field. The electrical field, the first term, if I look at the magnitude, the magnitude. So magnitude, so this is a constant, right? Because it has nothing to do with distance, okay? Then this equal to what, right? Okay, then we have only thing that change with distance is this term, okay, is this term, right? Because the first term doesn't change, this term is constant, okay? This is also constant. So we only need to look at how the magnitude change with the distance, with the distance, right? Then if this term reach to, this can be two extreme values, right? Two extreme value is +1 and -1. Do you agree? If the phase is 0 or 2 pi, okay, or n2 pi, okay, this is equal to what? If this phase equal to pi, this is equal to -1, right? So this is two extreme values, okay, the two extreme values. What is the between? This is just a complex number with the magnitude equal to 1. But we like to look at the extreme value because the extreme value for this term, we have 1 plus gamma and 1 minus gamma. You agree? So this is a maximum, this is a minimum, right? Okay, maximum value and the minimum value. So when gamma larger than 0, that means the eta 2 much larger than eta 1. So in this case, this equal to gamma, right? Okay, for gamma larger than 0. Then this equal to minus gamma for gamma less than 0, right? For gamma less than 0. So for gamma larger than 0, when the maximum value happen is, the beta 1 times z, okay, beta 1 times z, or maximum, okay, or maximum z equal to n times 2 pi, okay, n times 2 pi. 2 times, not 2 times, okay? That is, there must be 2 times, right? So this z, okay, from this value, z maximum, of course, this is a minus value, okay, this is a minus value. So the 2 and 2 canceled, right? So this is n pi divided by beta 1. So this is how we obtain this. So when n equal to 0, that means on the boundary, the electric field reaches to maximum, okay? The other way around is for the minimum value, okay? For minimum value, this must be equal to 2 times the beta 1, that minimum value, that must be equal to 2n plus 1 times the odd number times pi, okay, times pi. So at a different location, we can see the field reach to maximum, minimum, but the minimum not necessarily equal to 0, okay? And the other way around, if when gamma less than 0, okay, then the result is offset, okay? So therefore, we expect the electrical field, okay, electrical field in medium 1 for gamma larger than 0 on the boundary maximum, and we have another maximum, okay, this is all is the maximum, right, and the maximum, and this repeat every watt. This maximum value repeat every half wavelength, right? So every half wavelength that repeat, okay, right? Repeat is maximum. Then also you say we have maximum, we have minimum, okay? We have minimum. So this is happen that happen at minimum. This is for if gamma larger than 0, okay? If gamma less than 0, so all the result is opposite, right? All the result is opposite. Then this is a very significant. So we will see why it is very important. Okay. Similarly, you see, we can find the transmit field. The transmit field is understandable because once the wave penetrates into this, partially penetrate into the interface, and then we'll travel towards that direction infinitely large and never come back. So this wave we call, this is a traveling wave. This is traveling wave, right? This is traveling wave. When we say only one exponential term, this must be traveling wave. Now let's say in medium 1, when we say the total field, we have one traveling wave in that direction, another traveling wave in minus that direction. We know the total field will not be a traveling wave, that become a standing wave, or partially traveled, partially standing wave. Okay. one of the very important discussion I also should have here. We only have two discussions. We shall have a third discussion. Okay, this is a very important observation. The third, the third discussion is the maximum and the minimum of electric field occur at, okay, what? Occur at the reflection one reflection coefficient is real. Okay, one that happen, it is real. Why you see, if you look at the reflection coefficient, okay, so if I call this is a reflection coefficient, if I call this is a reflection coefficient, in general, sorry, not this. In general, this value is a complex number, all right? So it is a complex number. It is not complex number only when the phase is either 0 plus n to pi or pi plus n to pi, right? Okay. So that happens when the maximum value only occur at those very special point. Okay, very, very special point. And sometimes we calculate, this reflection coefficient using logarithm number, but we will discuss this in future. Okay, not now. Now we are also interested in, if we have interface, okay, along this direction, we like to know what is the total field divided by if this is in x direction, and the magnetic field is in y direction, okay, and for standing wave, in medium 1, right? In medium 1, this is what we are interested in. We give a name. We call this we call impedance. Okay, we call wave impedance. This wave impedance is different from intrinsic wave impedance. Is intrinsic wave impedance is for traveling wave. Okay. Wave impedance is for standing wave. We know what is the difference between traveling wave and standing wave. Traveling wave only has one exponential term. That means the wave propagate either in positive z direction or in minus z or in any direction, okay? But standing wave different. Standing wave is you have incident wave, you have a reflected wave. You add together. So this wave we call a total field, right? You have incident, you have reflect. This is total field. But traveling wave also can be total field. For example, the wave traveled and then transmit into medium 2, that become still a traveling wave, but it is a total field because there are no reflected wave. Okay, so for total field, the wave impedance, and we try to distinguish it from the intrinsic wave impedance. Then we emphasize for traveling wave, we call intrinsic wave impedance. Otherwise, we call wave impedance. Okay, wave impedance. Then when we have a total electrical field and a total magnetic field, okay, and total magnetic field, then we take, because we already have a mathematical expression for E field and for magnetic field, if we take a ratio of the magnitude, okay, the magnitude of electrical field in X component, magnitude of magnetic field in Y component, we take a ratio, we have a also quite simple mathematical expression, right? This expression, because we are talking about traveling wave, or talking about standing wave in medium 1. So it happens that proportional to the intrinsic wave impedance in medium 1, all right? Also, it is a function of reflection coefficient at the boundary, right? So we simplify this, okay? We simplify this in a general way is, if we talk about the wave without referring a specific coordinate, okay? Say, I don't like to say Z, sometimes X or sometimes Y, okay? Let's talk about distance, okay? So let's say if I observe the wave, L distance from the interface, okay? Then I replace everything minus Z, or Z equal to minus L, okay? Right? In our specific expression, right? Then we have more general expression is this total wave or wave impedance at L distance okay, L distance away from interface. What that is, that equal to this, or very simply equal to this. Okay, so I don't need to repeat, right? So the sine theta equal to okay, if you use very simple expression into this, okay, so into this, then we can find another. So if you prefer to use trigonometry function, that is the total impedance. So that means the wave impedance at a different location, a different value, and it's a complex number. Okay, it is a complex number. So it's changed. So it changed. Okay, so this is what I have. Okay, let me take a few more minutes. Okay, now I like to have a more general description. We had assignment last week, but probably many students haven't done it yet. We can write a general expression for electrical field, plane wave. This is a general, the general expression. So this means the magnitude plus polarization. Right? It tells you the magnitude, it tells you the polarization direction, arbitrary. Okay, arbitrary. Right? But it is a constant. So constant means it doesn't change with time, doesn't change with the location. Okay, so it never changes, right? Then exponential function indicates this is a Planck wave. Okay, then we have minus G. G means everything after G is a phase, right? We have K. K is wave vector wave number. Vector wave number. So because it's a vector, so vector I can decompose into 3 perpendicular unit vector. Okay, project to, right? Say if I still choose X, Y, Z, then the projection on X-axis, projection on Y-axis, projection on Z-axis. That means the wave will propagate in any direction. I can decompose into like a speed, right? Like speed, I can decompose into 3 components. That means that they have speed in X direction, speed in Y direction, speed in Z direction, and the total is the wave impedance, right? Okay, so we have the kx squared plus ky squared plus kz squared. Okay, so this take a square root. This is what we have. Also, all right. Okay, then this is what we call the wave impedance. Okay, the wave impedance. Not a wave number, vector wave number. So I dot product R. So R is the observation. The observation point, position vector. Okay, so R is X, Y, right? So the K dot R is a very concise expression. Okay, that means Kx plus Ky plus Kz. Now we use vector very concisely. We describe a general description of the wave. Then we had assignment. Then with the electrical field in this expression from Maxwell equations, you can justify K propagation constant always perpendicular to polarization vector of the electrical field. Okay, and also magnetic field. How to determine magnetic field is you know the propagation direction because K I write in K times K vector. Okay, K is the magnitude. Okay, so this is a unit vector. Okay, so if you know the unit vector and the cross electrical field, you have a direction of magnetic field. The magnitude of E over H follow Ohm's law. Okay, so this is a intrinsic wave impedance because this is traveling wave, right? Because this the exponential term is traveling wave. Okay, so this is a general expression for Planck wave. Okay, general expression. You see the wave propagate in K direction. Okay, then you can justify K perpendicular to E vector, and also because of this, K also perpendicular to H. So that means if you have E, okay, then you have H, okay, they all perpendicular to each other, okay, they all perpendicular to each other. All right, then this point is your observation point. Then why we call it is a plane wave? You say K, this is phase term, okay, phase term, the phase, K is a vector, R is a position vector. This equal to a constant. Check what you learn in three-dimensional geometry and for plane wave. This is a plane wave, a plane equation, okay? This is the general plane equation, right? So that means when phase equal to constant, this always exists in a plane, okay? So this is the equal phase. This is the equal phase plane. This is the equal phase plane. Okay, this plane is equal phase plane. All right, so that is we end up at here. You say we end up at the normal incident, and the case for oblique incidents, we just leave it to you. It's not a required. It's not required. A little bit more complex, but much more interesting. Okay, much more useful, and we will have a brief discussion in from 11:30 for the ESTR student. We will briefly discuss this, and then we also discuss if this is a multi-layer medium, what happened? Okay, and also very useful things. Okay. Okay, so we stop here today. Let me say I have some questions. Could reflect electrical field be opposite direction of incident? I think the question you're talking about, the direction must be polarization direction, right? Not the propagation direction, right? So when we have a reflection, the direction of propagation is always the opposite, right? Could reflect wave be opposite direction of incident wave? And the reflected magnetic direction remains the same. That, okay, this question, okay, this is a good question. And so what I suggest you is you ask Maxwell equation to answer you. Okay, you can ask Maxwell equation to answer you. If you give a minus sign, and then if you give a minus sign, and then you ask Maxwell equations, and then can you find a solution? Can you find a solution? Okay, because in our case, we assume electrical field incident wave has a polarization direction. We assume reflected electrical field in the same direction, right? Then we can find a solution. We can find a solution. And then you can ask Maxwell equation, substitute it into it, and to see if you can find a solution for reflected wave and the reflected magnetic wave. All right. And then have a try, then we discuss. Very good question. Yeah, I like student, you keep thinking, but not just simply just ask questions. Okay. Very interesting question. Maxwell equation can answer you. All right. Okay, let's stop here today.